Two things of homework coming back. There are exams here, some regraded. Well, let's see. I know. Did you? Where's? Yeah. Here. But I don't know if anybody else. Sean, do we have a new game going? Okay. Your identity's broken. Okay. Well, let's see. So I had one thing. This is sort of background thing. This is thinking about our two constituencies. That there's actually, a substantial number of undergraduates and graduates in the class, and so that's a little tough. If on average, if you're a junior. Typical undergraduate's a junior. There's actually a few, one or two sophomores and one or two seniors, but most people are juniors. And then otherwise, you're master's students or some sort of special program. So, consistent with what we usually do, there'll be some adjustment for that. So I should have said something about this sooner, before half the undergraduates committed harikiri in frustration or whatever. But anyway, so I'm going to deal with that somehow. So I haven't done that up to now. So I just have given you the grades means. I haven't separated anything, and I'm not doing that. But actually, the undergraduates are doing a little bit. It's not, individually, it's not clear where things are exactly. But on average, the undergraduates, sort of like maybe 7 or 8 point maybe mean below the mean. So that means you may do a little better than you're doing. Of course, if you're getting a 20, it's not going to help, whoever you are. If you're getting a 20, there's you should take extreme action, whatever that is. So, but anyway, some of the rest of you, that'll help. And okay, now the plan for today is I've been worried that I haven't confused you enough. And I'm going to confuse you for sure. I'm going to make a harder effort to confuse you. So so let's discuss, take a problem, and we're going to discuss a few problems, mostly as all around the same point, unless we get somewhere, we still have a large chunk of time to go before the end of the time when we've exhausted this topic. But this is one of the nice topics about renewal theory. It actually doesn't have that much to do with renewal theory per se. It's even more general. But let's start with a particular thing. So, and I'm going to want to think about, this is the thing where you're thinking about. So this is the experience that, we individually, each of us, realize that the world's against us. Things, for us, our experience is worse than average. When we go to the subway, right? When I go down the subway thing, all the people are coming right up out of there, which means the train just came, and I'm going to sit there for a long time, right? That's my experience. I go to the subway, and I'm going down, and all the people are coming up because that, and that means I just missed the train. Okay, so then you think, well, if I go out, if I walk to Broadway or Amsterdam at 1:16 and I'm looking for the bus, I'm looking for the M11 or whatever, and I'm going to take the bus, that I'm going to wait longer than average, right? So that's sort of the issue. So we're going to talk about that. So as the first thing is we have a model. So we're going to make a model of, here's time, and we're going to think of buses, say. So we take buses, it could be subways, and let's suppose, just so we're in the context of the course, let's suppose one model is that buses arrive according to a Poisson process. So we know how to think about that. Well, actually we want to treat also the case where we assume nothing about how the buses arrive. We think that we might be thinking about that they're somewhat scheduled, but they might fall behind schedule or get ahead of schedule or something like that. But there's so many buses we'll get to that. But we'll start with the easier. So from some point of view, easier is to assume that the buses arrive according to a Poisson process. Period. That's sort of, I mean, it's not more realistic for sure, but sort of easier because it's a clean mathematical model. So we sort of have, well, we could start anytime. This could be 0, and we have buses arriving. And these arrival times are supposed to be according to a Poisson process, which means that these intervals, say from here to here, and then x, these successive intervals, right, are, if I did a plus, these intervals would be an IID exponential, right? These, and if we counted the buses that arrived, we would make this counting process. So if we drew n of t, we would count the number of buses that arrive by time t, and we count like this. And then we have these intervals between. And now this is a sort of, we're talking about renewal process. A renewal counting process is this same n of t, but where these x's are again independent and identically distributed, but with some other distribution. And actually, even more generally, we could say that they're not necessarily independent. If we wanted to treat the actual, buses we would see, if we went out and studied this, you could do this. You could make this your extra credit project. This would not be a bad one at the last minute. You could actually, I mean, this would be tedious. This is sort of in the order of that article about, in the Spectator that hardly anybody missed, about the guy who said he's going to spend a week and, live without spending any money. So he was going to, he was going to borrow money, juggle, do stuff, raise money, which is sort of inspired, but this sort of invites that if you don't have some data source, you actually have to sit somewhere and watch it all, which is kind of, so a major problem would be how do you get the data efficiently, but otherwise you'd get to sit there for some period of time and observe it, which would be tedious. You might get picked up by the police before you got halfway through, or somehow as you'd be loitering, okay? But anyway, in our context, we have buses arriving according to a Poisson process. And the question is sort of, let's suppose there's some mean. So the intervals between buses are exponential with some mean m, like 10 minutes between the buses, right? Say, which is maybe about what they're supposed to be. And that might mean Poisson's not crazy. I mean, they sometimes come in bunches, and and sometimes they are spread out, and so forth. And so the question would be, you go to the, you're mostly a hard-working student, you're mostly sitting here grinding away, but at some time you decide you've had enough, you're going to go down to the village and do something, take the day off, and you don't do this all the time, so you just go there. You go to the bus stop, and you're going to wait for the bus. And the question is, how long are you going to wait? Well, your personal experience is whatever this is, you're going to wait more, right? That's sort of, that the buses are out to get you, and you're going to wait more. But let's just think about what is the answer. How long should you expect to wait? Right? And this is nice, concrete problems. So this was like the last exam. It should have been questions like this for the Poisson process on the last exam instead of those crazy, hard questions about the satellites, right? Whatever, that they're launching from Manhattanville, right? Okay, so answer 1. Let's just think about this simply, right? Not get all hung up in this stupid stuff we're doing in this course. The buses, the time between successive buses in this situation, they're independent and identically distributed, and the mean is m. The average spacing between the buses is m, right? You come sometime. So how long should you have to wait? Obvious answer is, well, if the average time between the buses is m and you come in the middle, it should be m over 2. Because the intervals are on average m, and you should wait half of that. half before you and half after you. Certainly for any interval, the amount before and after ought to be about the same. Sort of seems by symmetry, right? I mean, this is one argument. Now, the sophisticated thing I've been trying to sell here for the last few weeks is that if you come here, T, you come here, there is something called the lack of memory property. I mean, there's a whole bunch of stuff written in the book about this that says it doesn't matter what the past was because it's Poisson. So we have this lack of memory property. So this remaining distribution is exponential, just as if we started right here, as if the last bus was right here. So the fact, like if the subways were Poisson, and I saw the people coming out, I'd say, it doesn't make a difference. It's Poisson. The fact that the train just left now is, I'm not going to wait any longer. It's going to be, whatever. It's same. But this lack of memory says, lack of memory, I'm clever, lack of memory, even though the average distance is m, the distance is actually average. My expected weight is going to be m, not m over 2. Because it's a full exponential, this is a full exponential going forward, just as if I started. So this should make you unhappy. Of course, it's really great if you can somehow in your mental processes and your spiritual being can integrate these two answers and be totally comfortable with both of them. Right? Okay, this is good. If you can do that, that's sort of reaching a higher level. But anyway, the question is, what's going on here? Average interval is length m. You should be in the middle of some interval, so it should be this. Or lack of memory, it should be this. Now, I guess this chapter is important because this chapter says just drop this out, and you could ask the same question. So you say same question now, but we don't have the lack of memory anymore here, right? No, this part is so if we this argument didn't require any of this stupid stuff we're doing here about probability, so we got m over 2 fixed, so it doesn't matter. But here we're going to get something else. But what? And even better, we could drop this out. I mean, this part's not realistic. It certainly must not be the case that if you've had 3 buses in the last 2 minutes, that it's going to be the same to the next bus. Surely the buses are scheduled, and if they're bunched together, it's very likely it's going to be a lot longer to the next one than, if they're coming 10 minutes apart and you've had a couple of them right together, the next one's probably going to be further than 10 minutes, right? Because they're scheduled. So I want to allow here that they actually could be scheduled in any way, the real thing. They're somehow during the day. I mean, I'm going to assume a kind of a stationary situation where they're not building up in some crazy way. They're sort of just fluctuating there. They're probably the real thing. There's some sort of schedule, but they get off schedule. Maybe they get back on schedule. But actually, the renewal, our chapter assumes this IID, so that makes the theory easier to look at. But actually, interestingly, this is not required. But our chapter does this. But the point is, the distribution here, in this case, these x's, the probability that x is less than or equal to t, is now some CDF, but not necessarily exponential anymore. And you could keep this. So this is the cleaner math model of this section. Is there any way out of this? Does somebody want to volunteer how we should think about it? There's a fundamental idea here that's extremely important in this thing that actually, so as you can see, if it doesn't have any of this in it, it must not have too much to do with the fine details of this course. But it's actually, it comes into all these problems. So I invite a resolution. The resolution, I'm thinking of the resolution as actually not depending on the Poisson process, not depending on the renewal process, just depending on the common sense, well, but not all, if you don't think about it right, not obvious, what's the explanation of why you think it might be m over 2 or m? And which is right? I mean, if this answer, of course, is depending on Poisson. So if it's not Poisson, it'll be something else, and what would it be? So it could be here, it could be, so let me just put the cases. Poisson, renewal, general. Cases. Well, let's think about this backwards a little bit. I mean, I could be walking backwards, but the backwards I want to think about is actually this is sort of like, suppose the buses are scheduled and the subways, you know, they're scheduled actually. They're slightly off schedule perhaps, but they're scheduled. So that's actually the real thing. So the randomness, if there's not this assumption, and it's really scheduled and slightly deviating from the schedule, then the randomness isn't so much, the key randomness is not the bus arrival times, it's your arrival time. I mean, you're coming from here and you're going to the bus stop and you're not reading the schedule on the post, or you're just going there. You don't know the schedule in advance, so your arrival time is random. That's the real thing, rather than that the buses, they may be scheduled. So that actually, the randomness there is hard to figure out. Right? It's not clear. And so when you make a Poisson model or renewal process model, it may not be correct because the buses don't do that exactly. They're usually scheduled. So, but what is random is you're coming. So the bus times are all there like the X's. And you come randomly, boom, and pick T. That's what's random, right? That's the part we agree that if we don't plan this out, and we just sometime, 2 in the afternoon sometime, we just happen to after lunch decide to get on the bus. We don't know the schedule. We're just going there sometime, and then we're saying how long. And if you then, of course, there's a schedule there, and you could see sort of what you might happen from the schedule on the post, but if you just thought of this information, what would you have to wait? The point is, this arrival, this is what you should think of as random. That your time of arrival here is random. Somehow, and these X's are already given. They may be fixed, or they may be fixed and varied, right? That's sort of the real thing. But this is random. Now, if that's the case, then the thought is, now you ought to see that there's a reason for your bad experience. Because if you arrive at random, you're much more likely to fall in a big interval than a short interval, right? Whatever these intervals are, whatever these arrival times are, your random arrival is going to more likely fall in a big interval than a short interval. And for example, if this were like this, you're very unlikely to fall in here between these two clustered buses. So it looks really bad if the buses are messed up and they bunch together, right? A bad case. So let's say they're doing this, and then they somehow get bunched together in various ways, so that the pattern it was supposed to be like, not pretty. It was supposed to be like this. Somehow the traffic patterns, we wanted this, and we got this. They got bunched together. For some reason, things might happen like that. This is a little complicated, right? But suppose it's like this. So now you arrive at random, right? Boom! in here, right? You're going to be in here. You're not going to be in here, right? It has nothing to do with, that has nothing per se to do with the fine details of this course, right? I mean, it's just, but it has something important, is that you're sampling time at a time. It's a random time rather than one of these intervals, right? In other words, if you said, what fraction, what's the distribution of the time, and that's where the M came from, right? What's the distribution of the time between the buses? So you said, I'll make a histogram of these times, and you're going to get, if we use, you're going to get epsilon, you're going to get epsilon, epsilon, M, epsilon, 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 M, epsilon, right? Using epsilon for little things and M for big things, you're going to get a couple of little numbers and a big number and some little numbers and a big number and so forth. So your distribution of the times between the buses is going to have a lot of mass on little numbers and a little mass on big numbers, right? So that some of that. So the distribution, the histogram of the time between buses is going to be funny there. Here it's going to be almost constant, very different. So, but they might both have, if this is the same number of buses, the average is going to be M in both cases. If you started off with this many buses, they're 10 minutes apart, the same buses come, they just get bunched together, the average time between the buses is the same, because over some long time, there are 30 buses over several hours. And they all 30 come, and they're all there, so the average time, M, time between buses, average time is M, will be the same no matter what, for here and here. Okay? So if you were to say, what's the distribution of the time between buses, you'd get nearly deterministic here, and you'd get this weird distribution here. And if it was Poisson, you'd get the exponential distribution. And those distributions of those times will be different. But that's taking the point of view of, I go to one time, and I'm looking to the next time. So I'm actually looking at the points, the arrival points, and I'm saying, what's the time until the next one? So I sample at these discrete points and look at the next time. I don't sample at a time. So there's the sampling the time versus this looking at the successive buses. If you look at the successive buses, you get this distribution of these things. And if you look at the time, you're going to get something different. And if you look at the time, you're almost all going to see, in this picture, you're going to mostly land in have these long intervals. That practical story underlies a lot of stochastic. This is a big chunk of what's in Chapter 7, too. In Chapter 7, this stuff is under the section called the inspection paradox, which I think is 7.7. So that's telling you that this is the average time of the buses looking from bus to bus, but this is looking at time. So actually this is wrong, because if we come at a random time, it's not the random, this is the perspective of the buses. From one bus to the other, this is the average time. This is what half of. M is the average time between buses, and the interval you fall in is not going to be of length M. It's likely to be longer. So therefore, this is wrong. And this turns out to be, in the Poisson case, it explains this, why it's still M. The Poisson case comes out very naturally. In the Poisson case, going forward and backward, each has mean M. Right? The intervals themselves have mean M, but the Poisson case, the randomly selected one actually has mean 2M, which is very special because it's exponential, because it's M one way and M the other way. It's exponential in either direction, and it's 2M. But it could be different, and the real thing could be different. Okay, so we've been babbling on about this. Now the question is, well, this chapter addresses what to do if the distribution, if it's a renewal process. The times between the buses are independent and identically distributed, and then you think, well, you have some distribution for the time between the buses, and then what's the distribution of what you see at an arbitrary time? So you actually want to know, oh, this is true. The distribution of the time between the buses is some distribution. And then you want to know what's the distribution at the random time. Now, the interesting thing, which is somewhat difficult, is that actually this relationship between this and what was called the equilibrium distribution, another distribution that corresponds to what you see here, these two distributions, the relationship between these distributions actually holds without the renewal property. So that if you actually just went and took data on the bus times, you could actually go there. This is the point. You could measure, you could actually go and say what is, you could do this two ways. One way is you could go and look at for a long period of time and make a histogram and estimate this distribution, which would give you the distribution of the times between successive buses. Without any probability assumptions, you would accurately just say there was 3 minutes, 10 minutes, 1 minute. You just take it up and you make a histogram, so you're seeing this. You've done time, and then you have a histogram, so it's going to be fractions. It's going to be an empirical distribution, but it's going to go like. And so this is 1 and 0, and this there must have been 1, 2, 3, 4, 5, 6, 7, 8. In this example, there were 8 buses, and they arrived at this time, 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 and this time. And what you're seeing here is the proportion of the buses that arrived before T. I mean, in their interval. I mean, the proportion, I'm not saying this right, the proportion of the intervals that are less than T. This is an estimate, F hat of T. I'm looking at the proportion of buses, the proportion of intervals between buses that are less than T. Right? So this is meant to be the distribution of one of these intervals, either here or here, or here. So this one that we're looking, and then the actual thing would converge to something. So if it was Poisson, this would look like this, and this would be exponential, right? This would be f of t 1 minus e to the minus t over m, right? Would be the mean. So this would be the distribution. If it was exponential, this would be what you're seeing. And if you estimated it, you might see something, with a sample, you would see something that looks like this, right? You get something like that. So all I'm saying is the actual distribution might be exponential. If you sampled it, you get an empirical distribution that's the proportion of intervals you saw less than t, as opposed to the probability that an interval will be less than t. But this is sampling interval by interval, right? What I'm looking at here, when I'm thinking of f, I'm thinking of the distribution of one of these intervals, not at a random time t, but just starting at this point, what's the length of this? So I'm actually now sampling at the intervals. And if it was renewal, all these things are independent. But otherwise, I'm still going to be able to estimate. I'll get this proportion. I'll get f. So what I'm trying to say is if you look at this, you record this length, this length, this length, and if you did this and you got a lot of data, you would be saying this is the empirical distribution of the length of the intervals between buses. And you could, with lots and lots of data, you're going to estimate the true thing if it goes on and on and on. The question is, what is the relationship between maybe this should be x, not to confuse things, just think of this time. But what is the relationship between the distribution of these intervals and the time you would have to wait if you came at time t? That's the issue. And that's what this inspection paradox is about in its terms of, well, first, the most important thing is to realize, right, that we've been emphasizing that what you see at a random time is different than selecting a random interval length. That's your different sampling. If you pick an interval, you're picking one of these intervals. And you're essentially saying, if I wrote down 1,000 intervals, I'm giving you the distribution of those 1,000 intervals. That's what I mean by this. I've looked at 8 intervals, and I've said, well, one of them was this length, one was this, and so forth. And if they were exponential, it would eventually, as the sample increased, it would look like the exponential distribution. The question then is, that's saying how long are these distributions on average, but the question now is I come in at some random time, how long is this? And if it's Poisson process and this thing's exponential, this is exponential just like the interval distribution. But suppose the intervals are not Poisson, then what? Like if they're like this. If they're like this, you're going to see that actually there's going to be a big probability on larger numbers, because you're mostly going to come in the middle of one of these large things. It's going to, now what does that mean? What is this picture going to look like? If it was deterministic, let's just think of what do these things look like. If this was like this is number one. Number one is deterministic, nearly deterministic. So what does this thing plot? Right? Let's put x so we don't think of it as the other. We're plotting the probability that the interval's less than or equal to x. So it's not going to be small. So if it was exactly deterministic, there would be some deterministic value, which would be m, its mean. It would be 0 here, and then jump right up to 1 right here. Because none of them are less than m, but they're all exactly m. So this is a picture of a CDF of a deterministic distribution where they're all length m. So I'm just plotting a CDF. But if it was the second case, maybe is exponential. So the CDF then we know is this, where it's 1 minus e to the minus t over m, x. There's this x. Now, if it looks like above, if it's this thing, well, most of the time you're going to see that the thing in that, this is this bunched. Number 3 is the bunched. You're actually going to have the thing be some crazy thing like this, where it's still, if these are bunched far apart, there's still a significant probability that you're actually bigger than this value. Right? I mean, this is the probability that it's less than x. Well, the picture there maybe is making it grow a little faster, but it's not up here at the top yet, because they're long. What you're going to see is, what you see is essentially this, what, at a random time, and at a random time it's fairly long. So it's not going to be, it's going to be lower. This is essentially, it's going to be lower in that situation, because this is the probability that the weight is going to be less than this amount, and it's going to be not that big. Okay, the question then is, how big is it? That's the next level. That sort of first level is, it's bigger. The real weight here is bigger than it would be here. The second level is precisely what is the average weight, and what is the distribution of this weight. I mean, there's some chance it'll be very small if we fall in here, but that's not very likely, and it's some chance it'll be big. And so that's where the renewal theory comes in, and even the more general theory gives the same answer. So if we think about going forward, I've worded this that we're thinking about going this way. So that's, or here it would be this. So that's focusing on the residual lifetime. The time from some t forward to the next point, right? The time from t to the next point. Now we come back to where we were before. There's a standard approach to this problem, just like all these other renewal problems. There's a mantra. There's very limited things to think about. Average reward per cycle divided by average length of cycle. That solves all problems. So here you have cycles are where these arrivals are occurring. So let's think of, we're thinking about, suppose we think about the average. if we think about the average residual lifetime, we give ourselves rewards. So here we are, and here are events. These are the things. And then what we're going to do is give ourselves, we're going to try to capture what at time t, here we are, what's the time to the next point? So I'm just plotting this. Now we've got this residual lifetime, we might call it y of t. And we might say what we're really interested in is the residual lifetime. We want the residual lifetime so we want the long-run average of the residual lifetime. What I've done is plot the residual lifetime. Right? These are the points, and the residual lifetime is the time until the next point, wherever you happen to arrive. And we want the long-run average. So we can give ourselves a reward rate equal to this picture, the reward rate. And then we have the cycle. So let's go for that. Expected reward per cycle over expected cycle length. Now, here is some cycle, x. This is x. This is x minus t. Line goes down at slope minus 1, right? So the expected length of the cycle, this part is easy enough. Expected value of x. The cycles are, this x is this interval, which of course is random. So this is, I've just picked a big one, but the cycle is one of these. But the reward per cycle is this, what I'm going to get is, this is a reward rate, so I'm going to get the area of this triangle. So this is expectation of x squared over 2. And so then you're going to get this is what we've got here is the average weight forward. But x, remember, we've got this f of x is probability that x less than or equal to x. This CDF. It's not necessarily exponential. What would this be if it's exponential? If this is exponential, this thing ought to be just the expected value of x, right? If it's exponential, lack of memory, it ought to be the same. So if it's exponential, the second moment is twice the mean. If it were exponential, the second moment would be twice the first moment squared. And that would, lo and behold, when you divide by this, you get just what it should. In exponential, for an exponential, the second moment is twice the square of the first moment. So in the exponential case, this answer is just the mean. But it's not more generally. So there's two cases to think about. If it's not exponential, it could be not very variable. It could be like this thing here. It could be totally scheduled. So suppose it was deterministic. If it's deterministic, the nth moment is just the nth power of mean, right? If it's deterministic. So this would be, if it's deterministic, this would be the expected value of x squared. And so this thing would be 1/2. So if it's deterministic, it's like the original argument. If everything was deterministic, indeed, if you go at a random time, right? If you go at a random time, you're sort of, if this is not quite, but if it was exactly deterministic, these intervals are fixed, you're going to be in the middle, the average for you is going to be half of one of these intervals, which is what this is saying. If you make this second moment, if it's deterministic, the second moment is just the mean squared, and then when this cancels, it's going to be 1/2 the mean, right? On the other hand, if it's highly variable, like this thing is just going up, this is shooting up, skyrocketing to some large value, because if the second moment is huge, could be arbitrarily large, this thing can be really huge, regardless of what the mean is. This thing could be, it could be as small as half the mean. It would be exactly the mean for exponential, but it can be arbitrarily large if there's variability like this picture is showing. Now suppose, okay, so this is the answer. This is the answer of what we're looking at here is if we come at some random time, ka-chunk in here, how long do we have to wait? What's the expected wait we have to make? And the expected wait is this long run average of this thing, which in the renewal case, we know is expected reward per cycle divided by the expected cycle. And then this reward looks like this. At any time t, this would be what we'd wait. We'd take the average of this over this. So this thing is x, this is this area, which is x squared over 2. So that's this here. That's just this. And we're getting the average. We can also, by exactly the same method, but a very minor modification, we can actually compute the distribution. So let's suppose we're interested in estimating, let's say, FE x. We're going to call this distribution of this thing, we're think of y of t, well, this is the long run. This is the probability distribution of what you'd have to wait, or the long run fraction of that, of being, now this is being less than or equal to x. So probability, that if you came at time t in some random equilibrium time, that it would be less than or equal to x. So we want the distribution. So we're going to do the same thing, but we want the reward to be such that we only give a reward when it's less than or equal to x. So then we would go along here and we'd say, oh, well, I want to put an x in here, like that. And then I'm going to get a reward only when it's less than or equal to x. So I don't get any, so I get something here. Wait, I'm saying this wrong. Yeah, when it's, that's right, when it's less than or equal to x is this time. And then, of course, it's all of these. And then this part of this. Right? So what's happening here is here's the cycle. But if I'm only counting the times where it's less than or equal to x, I'm getting a reward of, I get a reward of 1 when I'm in here. Because I don't want this reward to be down here. I'm not going to take the average, but I'm going to say I get 1 here. So if I did this, the right picture, let me try to draw this again. I draw this, and I have some of these intervals, let me put a long one, short one, like this, and I've got some level here, x, and this goes like this initially, but this isn't going to be I initially have this, and I have this running across here. So in this interval, I assign here, oh, that's my reward rate, and then, see, here's a long one here. So this is going up. I make this. So in this cycle, here's a cycle, and I'm giving myself a reward here for when I have to wait less than or equal to x. I'm giving myself a reward here as well. So whenever this residual time is less than or equal to x, I'm giving myself a reward at rate 1 for whatever time that occurs. So I'm having expected reward per cycle, this part's the same, but what am I getting here? I'm getting the fraction of time that this is less than x, which is this part here. So this part isn't counting, but I'm getting this. So I'm getting here, this is occurring only if, well, let's see. So I'm getting it's a little confusing, but I get all of this. So if this interval is, I'm getting, right? I'm going to get, if this interval is greater than little x, my reward's going to be little x, because that's how much time I'm underneath. So if this interval is less than little x, I'm going to get the full interval. So if the interval is less than little x, I get all of it. So x is less, I get x. And if x is bigger than this, I get this. So this is, am I saying this right? Right here? Here's the interval. It's a long interval. For the long interval, I get a reward of this x, 1 times x, which is, this is x this way, this is x this way, little x. The interval's random this way. And then I'm getting a reward at rate 1 whenever I'm under here. So if big X is bigger than little x, I just get little x. If the big X is this interval, I get big X itself. I get the reward, the full thing. So getting 1 times x. So that's this. That's probably not a... So when you do this, you're going to get, this thing looks like this is the stationary excess distribution. This is Fe of x. So what I'm writing here is what you get from doing this. You get the distribution of what you would see. This is the probability that this random arrival at a random time would have to wait less than or equal to little x. And it's always this form. And it's expected value of this thing. So this, if I call xe, this is by definition Fe of x. And this thing looks like, let me put, and the expected value of this thing was what we had there before. This is what we had before. Now, let me try. I probably succeeded in my original objective to leave everybody in a state of utter confusion. The thing that you should think about here, what I tried to emphasize at the beginning is there's two different notions. There's the notion of these intervals and their distribution, and that's a random variable x with a CDF f. So you have all these intervals, like in all these pictures, and in the different pictures, these intervals may have different distributions. Like in this case, the individual distances, these intervals, tend to be nearly deterministic. In this case, they're highly bunched, so it has a very different distribution. F is very different, might have the same mean. But there is fundamentally an x and an f and a mean given. The mean may be the same in all these cases, but there's a distribution of these intervals taken from the point of view of how long is it from this point to the next point. What we want to know is this stuff. This is what we want. This is what we see at an arbitrary random time. We're saying what is the amount forward What's the situation looking forward when I go at a random time? At the very beginning, I tried to emphasize and communicate the main point. The main point that is key to understanding this whole stuff, at least the first step, is that what you see when you come at a random time is different than a typical interval. That's the essential first step, because then why keep computing if they're all the same, right? I mean, then this is saying what actually is the CDF, cumulative distribution function, of what you would see in equilibrium at a random time. A message is, without getting into too much detail, is there is a well-defined distribution for what you see at a random time that depends precisely on the data given to you. You're given that there's some distribution between these intervals, which you could measure for the buses. You could go out and make the histogram and find this F by just looking at the successive times between the buses, and this would be the distribution of those times. That's F, and it has mean M. If you now go at a random time, the distribution you'd have to weight is different from F, and it's going to have a different mean. It's not this. It's going to have a distribution FE with mean ME. I've used this notation to say what happens in here, and this is the ME, the mean, and this is a distribution. The main idea is not the specific formula, but first that this stuff that describes the distribution of intervals is different from this, and that there is a way of taking F to construct these. This stuff is just a function of F, which happens to hold even if it's not renewal. So if you went out and measured the distribution of the buses, you would find this directly. Given this is the distribution of what you would see at a random time. If that F was exponential, these two agree. So there's a theorem sitting there in the background. Theorem FE equals F. But if and only if F is exponential. So when F is exponential, what you see going forward is the same as what it would be from the interval point of view, which is actually getting you M, not M over 2. The mean of this is M. The mean of this is M. Therefore, the mean of this is M if it's exponential. But otherwise, it's something different. So the main point is not so much that you know exactly this formula or this formula, but you know that there are such formulas. And actually, this stuff is discussed throughout Chapter 7. So you'll be seeing discussion of the age and the residual lifetime. Age and residual lifetime. And you could be talking about the full lifetime. This is the length of the interval that you see at time t going forward and back both, right? So you say, well, how long was it? When you go, how long was that interval, both forward and backwards? And this is going forward only, and this is going back. So if you did the process, if you were doing the age and you had these things here, and you were drawing the picture, the age, assuming this is a year, the age would be this. Right? This is the picture of the, this is a time, and the age would look like this, because this is the time since the last point. So, it's here at t, it's this time, this time. This is how long it's been since the last point. The residual life, which we were just doing, is this thing. Right? The residual one is counting how much forward. So if we drew the same picture here, we put the same x's here, the residual life would be time forward is this, right? So I did it like I had just had. This is the residual life. This is how much time to the next point. And if we talked about the length of the thing, if we talked about the total lifetime would be constant in this interval. So if we would make this look, it would look like this. These flat lines is actually this is a of t plus y of t, right? If you think, well, you arrive at time t, what's the length of the lifetime, of the whole lifetime? Well, it's the age going back plus the residual time going forward. And since one goes up and the other goes down, of course, the age of that interval remains constant throughout this interval because the interval length isn't changing. I mean, the backward time is going up and the forward time is going down, but the total length is constant. So these processes, age is the one that goes up, residual goes down, and the lifetime's constant, but changes as you change intervals. So this in the total lifetime, during this interval, this lifetime is constant, which is saying if you arrive at t, how long is this interval here? Well, it's the same as here. It's the same interval. And then as soon as you change here, it'll be a new height. And you're talking about, when you do the renewal theory, you're finding stuff, what's the average age, what's the average residual life, what's this? And all this stuff fits in this framework of renewal reward processes, average reward per cycle, average length of cycle, which you're going to get in various ways. So this is a sort of a summary of it, though, because when you look at the mean, you actually get a very nice, simple formula about whether this mean is big or small. So let me just focus on this. Not too much, but this is this formula we had before. So what I want to do is think about this from the point of view, well, I think a good way is to think about if we did variance. So let's think of this as variance of x plus variance of x plus the mean of x squared, right? Over, so I've just rewritten that. And I might write this as variance of x plus 1 over, let me see if I write it this way. Variance of x over expectation of x squared Now, what am I trying to do? Do I know what I'm trying to do? I guess the thing you want to see is you want to see this thing in a simpler form. And the way to think of it is this should be proportional to the mean. In other words, there's a mean that's just the time units. Fundamentally, there's some units on this axis, and I've got a mean in the background is a mean m, which is the mean length of the cycles. And that depends totally on the time units I use, right? So m, I could change the scale, I could change the units and it would change. So it ought to be that this is just proportional to m somehow, and I should think of it that way. So I want to factor out this mean, which is just the scale. So this is the mean times something. And I want to get scale out of the picture. So this is actually like physics, you want to get rid of the units. You want to see that the mean cycle length embodies the time units, and you factor it out. So this is this. Here's the mean. So it looks like this ME is M times this, relabeled. So in this process, I first rewrite this as variance and mean squared, so I'm just rewriting the second moment in terms of the variance. But then when I've got this here, I'm thinking I want to factor out the mean because it should be proportional to the mean. That's the choice of the units. So when I do that, this term has variance of x over 2 mean squared because I took this out. This thing was mean squared over mean, but when I factor this out, it's just 1/2. So then this thing this mean that I'm calculating is the original mean times something here where the c squared is this. Now this looks crazy, but this is actually, you should all know this. This is how do you think about variability. And you want to think about variability not in terms of the variance or the standard deviation, but in terms of a scale-free thing that's independent of units. You want to think, how variable is a distribution? How variable is the exponential distribution? If I tell you the exponential distribution has variance 32, if I tell you some distribution, some random variable has variance 32, what do you know about its variability? It could have been constant with that. You could have the second, in other words, you don't know anything about the variability just by giving the variance or the standard deviation. But once you know the mean, you can begin to think of the variance in relation to the mean. And that's what this is. If you take the variance and divide by the square of the mean, which is the same thing as taking the standard deviation in dividing by the mean, this is a quantity without units. Now, what do I mean? If we multiply x by a constant, the variance will be the square of this thing. So the constant will be squared, and it'll be the same down here. So with this, c squared is unchanged when you multiply the random variable by a constant. So it's the way you want to measure variability. So for exponential distribution, the c squared is 1. The ratio of the variance to the square of the mean is 1, because in exponential, the variance is always the square of the mean. So for an exponential distribution, c squared is 1. For a deterministic distribution, c squared is 0. For a highly variable distribution, c squared could be arbitrarily high. And what I was saying before is in the deterministic case, this mean was half this one. And that's just this. You plug in 0 here for the deterministic case, and you see half. You plug in 1 for the exponential case, and you see that this is 1. And this shows you the extent to which this mean is different from this one. In a very simple way. Regardless, the units are all here. And they're captured again here. And the units are whatever units you do, there's a relationship between this mean and this mean. But this extra stuff is how much variability. What's the variability doing? So let's, in a few minutes, you might think about how you could affect the bus system. So, you've got a bus system like one of these buses here, and you're thinking about it, and maybe it's subject to some control or not. So you might have two things you could achieve. You've got this route's got 30 buses during the day. And maybe they kind of go like this instead of this. So your expected weight, c squared, is big, so you plan this is 10 minutes, but this thing might be 4. So you think it's reasonable that somebody should wait 10 minutes, but if this is 4, the real expected wait will be 40 minutes. Not just for bad luck, that will be the average wait. If this is 4, if this is 10 minutes, this will be 40 minutes. If this part is 4, whatever this is, if this is 10 minutes, this will be 40 minutes. Your job, perhaps, is there are 30 of these buses coming during a 6-hour period, and your job is to make the wait reduced for the customers. I mean, they're waiting 30 minutes, and you want them to wait less often. One solution is to have more buses. I mean, you might think, the point that's really important for this course is you might think that the only solution to reduce the average weight is to have more buses. There might be 30 buses in a 6-hour period, whatever that comes out to. There's some average time between buses, and that will be this. You'll get this M. And so if you put twice as many buses, this will be cut in half. However, without adding any buses, if you could change this, if this was 4 and you made it 2, in other words, if this was 4, this is 10, and this is 4, and you wait on average 40 minutes, you could cut it in half by doubling the buses. Right? Cut this, make this half. This will become half. On the other hand, without changing the number of buses, you could cut the variability. Well, you have to figure some way not to let this happen. Right? You're thinking, what do you do to make prevent them from bunching, right? But that's actually, the point is that part of the problem, a significant part of the problem, is probabilistic, which is why you're here. I mean, why we're doing all this stuff, is that it's not just more buses, right? And if you don't know this stuff, the only answer you can imagine is that it's more buses. I mean, if your average wait is 40 minutes, you look at, I mean, it's a little crazy. You might sit there struggling. The average time between buses is 10 minutes, but the average wait is 40 minutes. Yeah, probably if you measured this correctly, there's a good chance you've got this job, you're interning to help solve the bus problem. People are complaining like mad, but they know the average time between buses is 10 minutes, so what, if people are crazy, there's no reason for them to complain, right? This is back to where we started, right? The average time between buses is 10 minutes. How could there be a problem? All these complaints we're getting, totally nonsense, because the average time between buses is 10 minutes. You know, though, from this, you know that it could be that the average wait would be 40 minutes, because this factor that counts the variability might be 4. Then the average wait is 40 minutes. If you, as a designer or as a decision maker, knew that the average wait was 40 minutes, you might say that was intolerable. If you thought it was 10 minutes, you'd say people shouldn't be complaining. Somewhere in there, then the solution might not be to spend up to $1 million doubling the number of buses. The solution might be to reduce variability, which should resonate with the same stuff you get in production, all these other courses we do. This theme here on this point is critical, like it's fundamental to production and everything else, where the issue comes up that the stochastic variability is affecting the performance significantly. And this one example really captures, in a way that you can see it, how variability is affecting performance in a sort of simple way that if you don't look at it right, you won't see it all. I mean, this average weight is these two things, and there's this piece, but there's this piece. And this piece is not too complicated mathematically. It's a simple formula, but there are these two components. And the idea is to also pay attention to this. It seems at this juncture that we are in extreme need now. Having succeeded in reducing everybody to a quivering mass of confusion, we are in need of sustenance. Sustenance, right? Staggering forth. Okay, let's stagger forth and get sustenance. Yeah. Thank you. This is a plea. The Engineering Council is visiting our department today. There's a need for some students to tell them all the things that need to be improved. And we can think of some, we won't go into it, but anyway. So there's actually, if I get it right, at 1 o'clock, there's going to be interviewing graduate students. And at 1:45, they're going to be interviewing undergraduates. As of a couple of hours ago, there were like 2 people signed up for each. What we need or would like is like a total of 4 or 5, not 2. So if 1 or 2 people, graduates at 1 and undergraduates at 1:45, that would be good. And it's your chance to actually provide constructive input. Like, fire Professor Witt now, whatever input. But actually, it would be it would be very good. So this is a chance. This is actually a chance to influence how we do things, which everything's perfect, and we couldn't do any better.